This video is a review of the solid liquid solutions chapter of chemical thermodynamics. So we can define three different types of metrics for the concentration of a solute in a solution. One is mole fraction, which is the number of moles of the solute divided by number of moles of solvent plus number of moles of solute. We have the molality, which is equal to number of moles of solute per 1 kilogram of solvent. When we have molarity, or C, the molarity of a solute is equal to its number of moles per 1 liter of solution. And we can define different activities based off of these different concentration metrics. We can define activity based off of mole fraction, which approaches the mole fraction as mole fraction goes to 0. The molality activity approaches the molality as molality goes to 0. And you have the concentration, the molarity activity. The molarity activity approaches the molarity as the molarity goes to 0. So sometimes solutes are not volatile, meaning that they have no appreciable vapor pressure at a given temperature. And when you don't have the vapor pressure, any vapor pressure to measure for a solute, that kind of throws a wrench in the works for our expressions for its chemical potential. So we want another way of determining the chemical potential of a solute which isn't volatile. So we can define the osmotic coefficient phi here. And the osmotic coefficient is minus natural log the activity of the solvent divided by molality of the solute times the molar mass of the solvent. So the activity of the solvent comes from measuring its vapor pressure, which we can do very accurately since the solvent is, almost has a mole fraction of 1. And we get this osmotic coefficient. And this osmotic coefficient is equal to 1 if your solution is behaving ideally at a given mole fraction or a given molality of solute. So this allows us to calculate the natural log of the activity coefficient of our solute from the osmotic coefficient, which is derived from the activity of our solvent, which comes from the Gibbs-Duhem equation. So this natural log of our activity coefficient of our solute is our phi minus 1 plus the integral from 0 to the molality of the solution of phi minus 1 divided by molality integrated with respect to molality. So measuring the vapor pressure and thus activity of our solvent, we get the activity coefficient of our solute. Colligative properties are those which do not depend upon the identity of a given solute. They only depend on the concentration of the solute. And some colligative properties include freezing point depression and boiling point elevation. So in freezing point depression, you have the change in the freezing point or the melting point of a solvent is equal to the negative, there's some coefficient, some constant here, a negative constant times the molality of the solute. So it doesn't depend on what the solute is, it just depends on what its concentration is, what its molality is. And this freezing point depression constant is equal to molar mass of the solvent times the gas constant times the normal melting point of the solvent squared. So this standard T fusion here, just the temperature at which it melts when there's no solute present. And all of that divided by the molar enthalpy of fusion for the solvent. So how much heat is released during melting, or how much heat is absorbed during melting for the given solvent. Same thing with the vaporization. So the temperature change of vaporization is equal to the boiling point elevation constant times the molality of the solute. Notice that the freezing point gets depressed, but the boiling point gets elevated. And this constant is equal to the same value as the freezing point depression constant, except for that instead of the temperature of fusion, the melting point, you have the temperature of vaporization, the boiling point. And instead of the enthalpy of fusion, you have the enthalpy of vaporization, the heat you need to go from a liquid to a gas. And a third colligative property of interest is osmotic pressure. We have the situation of a solution which is much more concentrated on one side than another of a semi-permeable membrane. A semi-permeable membrane will allow water to diffuse back and forth, but it won't allow this kind of green solute, which is very concentrated over here that I've drawn. The solute can't diffuse back and forth. So what happens is, over time, the water diffuses over here to make the solute more dilute, and what happens is you build up a difference in height of the two columns here, and that results in a difference in pressure between the two sides. And that difference in pressure is called osmotic pressure, where we reach an equilibrium between the sides. And the osmotic pressure is just equal to the molarity of the solute that is dissolved over here. Molarity of the solute times the gas constant times temperature. So once again, it doesn't depend what solute we have over here, it just depends what the molarity of the solute is over some dilute region. We can also define the activity for electrolytes, which are substances that dissolve into ions upon going into solution. So we have some hypothetical ion here, X nu plus, Y nu minus, and that dissolves into nu plus X ion, cations, and nu minus Y anions. And the activity for such an electrolytic solute is equal to the mean ionic activity, A plus minus, to the power of nu plus plus nu minus, so the sum of their stoichiometric coefficients, which is also equal to what we define in that video as the cationic activity times to the power of its stoichiometric coefficient times the anionic activity to the power of its stoichiometric coefficient. And the activity for these electrolytes is given in dilute solutions by Debye-Huckel theory, or the Debye-Huckel law, which says that the natural log of the mean ionic activity coefficient is equal to negative the charge of the cation times the charge of the anion times the Debye-Huckel screening length kappa divided by 8 pi times epsilon naught times the dielectric constant of the solvent, which is usually a number between about 1 and 100, times the Boltzmann constant times temperature. So this Debye-Huckel screening length kappa is equal to 2 times charge of the electron squared times Avogadro's number times 1000 times the ionic strength divided by epsilon naught, the dielectric constant of the solvent, times Boltzmann constant times temperature. And all of that to the power of 1/2, taking its square root. And then finally, going all the way down to the bottom of the rabbit hole here, we have the ionic strength, which is equal to 1/2 times a sum over all of the ions integer charge squared. So, for example, sodium would be a +1, calcium would be a +2, fluoride would be a -1, etc. The integer charge of the ion squared times the molarity of that given ion. So we can calculate from the molarity, the ionic strength. From the ionic strength, we go to the Debye-Huckel screening length kappa, and then that helps us get to our mean ionic activity coefficient, which gets us to our mean ionic activity, which is going to tell us all kinds of things about the reactivity and the Gibbs energy of the electrolytes.